Next week, we talk about the conditional random variable. And then we learn the conditional PDF and conditional CDF. And then here, if I have two random variables, what is the conditional PMF of two random variables? So here, from this definition, you can see x given y. For this PMF, x given y, we fixed y. So y is fixed. No randomness with y. So this probability is for x, not y. Therefore, when we take the marginal PMF with respect to x, well, we sum all x out, then we can get 1. But if you do the y, it is not 1, okay? Because y just fixed. It is a specific value. So here, let's see this example. I have a joint PMF. Joint here is in the following table. Then for this joint PMF, I want to find the marginal PMF and also the conditional PMF of x given y equals 1. So now, for x equals 1, if we want to find the marginal PMF of px, so I want to know when x equals 1, 2, 3, 4. So when x equals 1, that means I only see this part, the first row. Px1, that's the summation y. That means I don't need y, so I have 1 and y. So what does that mean, 1 and y? With different y, my x is fixed to 1. So here I have 1 over 20 plus 1 over 20 plus 1 over 20 plus 0, and you get 3 over 20. This is px of 1, x, 3 over 20. And similarly, you get a marginal PMF of x at 2. So x is 2, and for different y, I have 1 over 20, 2 over 20, and just the second row, so here this is x at 2, that's 6 over 20. When x equals 3, and when x equals 3, do the summation. So for the third row, that would be 1 over 20 plus 3 over 20 and 3 over 20. Last one, 1 over 20. It is 8 over 20. The last one, x equals 4. So similarly, we sum the fourth row. That is 0, 1 over 20, plus 1 over 20, plus 1 over 20. That will be 3 over 20. So here you have 3 over 20. Now, that is your marginal PMF of x. 3 over 20, 6 over 20, 8 over 20, and 3 over 20. Then you can check if using the property of PMF, the sum of this PMF is how much? That is 1. Similarly, we can also find the marginal PMF of y. So apparently, if we see the first column, that is the PMF of marginal PMF of y at 1. And you can see that this is 3 over 20. And the second column will be the marginal PMF of y at 2. That's 7 over 20. And the third column, marginal PMF of y at 3. That's 7 over 20. And the last one, fourth column, marginal PMF of y at 4. That's 3 over 20. And overall, this summation is also 1. Right, from the properties of the PMF. Okay, so now let's see the conditional PMF. So we have the marginal PMF of x. Now how about the conditional PMF of x given y equals 1? So y equals 1, that's fixed. Then the conditional PMF is the joint PMF x and y equals 1 divided by the marginal PMF of y at 1. So the marginal PMF of y at 1, we found that the green one, the first column, it's 3 over 20. So 3 over 20. And then the joint PMF of x and y equals 1. Maybe this first column. So we have 1 over 20, 1 over 20, 1 over 20, and 0. So we have either 1/3 when x equals 1, 2, and 3. And when x equals 4, it's 0. So here's a note. If you do the summation of y, the summation of x to the joint PMF overall, it should be 1. That's also the property of your PMF. Now let's see the conditional PMF. Here is y given x. Okay, so for y given x, first, if x equals 1, then we have joint PMF. First, joint PMF at 1 and y divided by the PMF marginal PMF of x at 1. Then the joint PMF x is 1 and y, then we have 1 over 20, 1 over 20, 1 over 20, and 0. And the marginal PMF of x at 1 will be 3 over 20. So x at 1 here. This is like 1/3, 1/3, 1/3, 0. So here we also have 1/3, 1/3, 1/3, and 0. So this is also either 1/3 or 0. When y equals 1, 2 or 3, that's 1 over 3. Otherwise, it's 0. Now, similarly, let's find the the conditional PMF of y given x equals 2. If x equals 2, we have 2y, and then divide by so here 2 and y, that's the second row. Okay, so for the second row, we have 1 over 20, 2 over 20, 2 over 20, and 1 over 20. So we will have 6 over 20. So here we have 1/6 and 2 over 6, 2 over 6, and 1 over 6. So this is either 1/6 or 1 over 6 or 2 over 6. When y equals 1 and 4 is 1/6. And when y equals 2 and 3, that will be 2 over 6. And similarly, let's quickly go through another two conditional PMF at x equals 3 and also x equals 4. So it will be 3y divided by the marginal PMF of x at 3. So we have 1 over 20. 3 over 20, 3 over 20, and 1 over 20, over 8 over 20. You have 1/8, 3/8, 3 over 8, and 1 over 8. So it is either 1/8 when y equals 1 and 4, or 3/8 when y equals 2 and 3. it's 0. The fourth row, 1 over 20, 1 over 20, and 1 over 20, 3 over 20. Then we get 0, 1/3, 1/3, and 1/3. So it's either 1/3 or y equals 2, 3, 4, and 0 when y equals 1. So for the summation, the conditional PMF of y given x, in this case y given x, similarly, we can check this should be this should be 1. First, let's see if my x is 1. If I fix x to 1, what is the conditional PMF of y given 1? Y given 1. That's here. So you get 1/3 plus 1/3 plus 1/3 and 1 no more plus 0, you get 1. When x equals 2, also when x equals 2, then if I do the summation, it'll be 1/6 plus 2 over 6 plus 2 over 6 plus 1/6. That is also equal to 1. So similarly, for x equals 3 and 4, we have 1/8 plus 3/8 plus 3/8 plus 1/8. That's 1. And the last one is the same. 0 plus 1/3 plus 1/3 plus 1/3. It is all 1. How about the other way around? In this case, still the conditional PMF y given x. But if I do the summation for x, if I do the summation for x, I have, in this example, x term is from 1 to 4. So y given x prime will be y given x first, or y given 1, and then we have y given 2, 3, and 4. Let's just fine. Y given 2 and y given 3 and y given 4. Let's go back to C. Okay. So now let's find the conditional expectation. Y given x and x equals 1. That means I consider all. So consider all, that is y from 1 to 4. Possible outcomes y. The associated weighting, that's conditional PMF of y given x. And here is y given x equals 1. So you have 1 times 1/3, and 2 times 1/3, 3 times 1/3, and 4 times 0, you get 2. Okay. Now, for next example, I have two random variables, x and y. So y is either 100 or 1,000, 10,000. And then x is with related to y. So x is either 10 to the minus 4 times y, or 10 to the minus 3 times y, or even 10 to the minus 2 times y, with the different probabilities. I want to find the conditional PMF of x given y, marginal PMF of x, and the joint PMF of xy. First, let's find the conditional PMF of x given y. We know that for the conditional PMF here, x given y, y is fixed. So y is either 100 or 10,000. So first, we can see the y is equal to 100. So if y is equal to 100, we will bring y here, so you need to times 100 here, and also 100 with the probability 1/2, 1/3, and 1/6. So here we have 1/2 if the x is 0.01. Probability 1/2, and then 10 to the minus 4th times 100, so 0.01, or 1/3 if x is equal to 0.1, or 1/6 when x equals 1. Then the next is the y, when y equals 10 to the 4th. When y equals 10 to the 4th, also now we can replace y to 10 to the 4th, and then we will get either 1, 10, and then 100. So it will be 1/2 if x equals 1, or 1/3 when x equals 10. Or 1/6 when x is equal to 100. And then since we have this marginal, this conditional PMF, we can find the joint PMF. So how do we find the joint PMF? A joint PMF can be found here. So remember, for the joint PMF, think about the conditional PMF, x given y times the marginal PMF of y. So first we can find when when y equals 100. So here 100. That means the conditional PMF of x given 100 times the marginal PMF of y at 100. So here we have 1/2 times 5/6 when x is 0.01, or 1/3 times 5/6 when x is equal to 0.1, or 1/6 times 5/6 when x is 1. And then when y equals 10,000, similarly, you get 1/2 times 1/6 when x equals 1, or 1/3 times 1/6 when x equals 10. When x equals 100, it'll be 1/6 times 1/6. So now we can find the joint PMF. So for the joint PMF, here's the table. Y is either 100 or 10,000, and x is either 0.01, 0.11, 10, and 100. So let's fill in. Here it should be 0. When y is equal to 10,000, I only have values of x at 1, 10, 100. So if x is not those three numbers, I should have 0. Similarly, for y equals 100, then once we have the joint PMF, we can find the marginal PMF. For marginal PMF of x means that I don't need y, so I will just sum y out. So the px, I don't need y, so I do the summation for y. So x will be either 0.01, 0.1, 1, 10, and 100. So those 5 different numbers, we have their PMF individually. When x is 0.01, that is 5/12, or 5/18 when x equals 0.1, or 2/9 when x equals 1. And when x equals 10 and 100, we just found that it is 1/18 and 1/36. Then the next, we will talk about the conditional PMF of 2 random variables rather than just 1. I did for continuous case. All right, let's continue. Next, we just talk about the conditional PMF. And how about the conditional PDF? So here is a conditional PDF of two random variables. So here's a definition. For the two continuous random variables, the conditional PDF of x given y will be also the joint PDF divided by the marginal PDF of y. And here's an example. This is our joint PDF. And I need to find the conditional PDF of x given y and also conditional PDF of y given x. So no matter which one, I also need the marginal PDF of either y or x. Right, so let's find the marginal PDF of x and also marginal PDF of y. So the marginal PDF of x and y so for x, marginal PDF of x, that means I don't need y, so I will integrate y out. So I have an integration and the joint PDF, and we do the integration with respect to y. So for y, the bound is from 0 to x. So here my integration is from 0 to x. And the joint PDF will be 2 times e to the minus x times e to the minus y dy. So we have 2 times e to the minus x and 1 minus e to the minus x. And the marginal PDF of y, that means I don't need x. So I will integrate the joint PDF with respect to x. And for x, my range is from y to infinity. So here is from y to infinity, 2 times e to the minus x, e to the minus y, dx. Then it is 2 times e to the minus 2y. Then we can find the conditional PDF of x given y and also y given x. Therefore, f of x given y that's the joint PDF divided by the marginal PDF of y. So we have 2 times e to the minus x times e to the minus y divided by 2 times e to the minus 2y. So here is e to the minus x plus y. And x is greater than or equal to y. That's the conditional PDF of x given y. And for y given x, let's join PDF divided by the marginal PDF of x. 2 times e to the minus x, e to the minus y, divided by the marginal PDF of x. So here is e to the minus y divided by 1 minus e to the minus x. And the y is between 0 and x. Okay, now since we know the conditional PMF and also conditional PDF, then next, how do we find the conditional expectation? Here's the definition of the conditional expectation for discrete case and also continuous case. So first, that's the discrete case. The second is for continuous. So the expectation of x given y, and now this given y is fixed. For discrete case, consider all possible outcomes times the corresponding weighting. That's the conditional for continuous case, x given y equals y. That is also consider all possible outcomes times their corresponding weightings. You see that for this conditional expectation, x given something, and this is fixed. Okay, we need to fix y to find the conditional expectation. For this conditional expectation, the expectation is taken over x or y. Here should be x, because y is fixed. And random variable y is fixed. So there's no randomness associated with y. So the result of this conditional expectation is a function of x or function of y. We know that for the expectation of x, finally this is a constant, right? So now if I given y equals a fixed y, then finally this is a function of y. Because the random variable x has been eliminated by expectation. So here we have a total law of total expectation. This is the conditional expectation of x given y fixed. And how about the expectation of x? So here we also have discrete case and continuous case for the law of total expectation. We said the law of total expectation for a discrete case, that is, I need x, right? So here, I take the conditional expectation, and finally, this will be the function of y. Then you times the PMF of y, and sum the y out. That will be the expectation of x. Here is the proof. What is the expectation of x? We know the expectation of x is to consider all possible outcomes times their corresponding weightings, PMF of x. So what is the PMF of x? PMF of x is, you can consider it as a marginal PMF. So marginal PMF of x, how do we get the marginal PMF of x? If I have a joint PMF. When I have a joint PMF and I sum y out, then I will get the marginal PMF of x. So which means this, I have the summation of my joint PMF and sum the y out. So here I have a double summation x and y. And what is the joint PMF? I can rewrite the joint PMF as the conditional PMF x given y times the probability, well, the PMF of y. You need rearrange the summation. So for summation x times the conditional PMF of x given y times the PMF of y. And for this part, again, this part, consider all possible outcomes times the corresponding weightings. This is the expectation of your x given the y fixed. So that's why we have the formula for discrete case. That is the total of law of total expectation. And similarly, you can apply it for the continuous case. So now let's see. Continue to our previous example. Let's find the conditional expectation x given y equals 10 squared or y equals 10,000. Yeah, we haven't found the conditional expectation. So now we have this table, okay, for the PMF, the joint PMF. So what is the conditional expectation? So to find the conditional expectation, we need the conditional PMF. So here, this conditional PMF, we need x given y. So we actually know the x given 10 squared and also x given 10,000 are. So here we just write it down. To find the conditional expectation, then we need to know the conditional PMF. So the conditional PMF, first, x given y equals 100. We found that from the previous example, 1/2, 1/3, 1/6, and 0, 0. And then conditional PMF at y equals 10 to the 4th. That's 0, 0, 1/2, 1/3, and 1/6. Then we can find the conditional expectation. So the conditional expectation of x given y equals 100. That is the consider all possible outcomes times their corresponding weighting x given 100. So you will get 10 to the minus 2 times 1/2 and 10 to the minus 1 times 1/3 and 1 times 1/6, you get 123 divided by 600. Similarly, for the conditional expectation, given y equals 1,000, consider all possible outcomes times their weightings. You have 1 times 1/2, 10 times 1/3, and 100 times 1/6. Then you have 123 divided by 6. Then with these two conditional expectations, what is the expectation of x? With these two, we can have x given y equals square, 10 squared times their PMF at 100, and plus the other term, y equals 10,000 times their PMF at 10,000. So get 123 divided by 600 times 5/6. And also 123 divided by 6 times 1/6. Okay, next example. If you don't have any questions about this, I have my joint PMF of xy, and I want to find the conditional expectation of y given x fixed. So in this case, this type is a conditional random variable. So I need to find the conditional PDF because I consider all possible outcomes times their corresponding weightings. There will be the conditional PDF. So how do I find the conditional PDF? First, I have a k here. K is a constant. So what is k? To have this joint PDF be valid, then we can find the constant k. How? Using the properties of the PDF. First, we need to solve the k. To solve the k, we take the integration. This integration should be 1. That's useful property of the PDF. So you get k times region. This region is here. And then we can plot this region first here. And this is 1. Here is 1, 0, minus 1.
はい。
So this is the area, k times the area. So it will be k times triangle, so 1/2 times the base and the height. Oh. So it should be 1. Therefore, k should be 1. Now, how do we find the conditional PDF of y given x? Need to find f of y given x. So by the definition of conditional PDF, y given x means the joint PDF of xy divided by the marginal PDF of x. So for joint PDF of xy, is k times the region. Here the region we can write it down as the indicator function 1, and the x is from -1 to 1. And for y, that is right. The x is from -1 to 1. And for y is from square root absolute value of x to 1. And what is the PDF of x? We can think about the PDF of x as a marginal PDF. So if it is a marginal PDF, how do we get this marginal PDF? If we have a joint PDF xy, then we sum y out, so we integrate y out. Here, the numerator is still the same. Okay, it's just like an old region. And then denominator, that is 1 minus square root of absolute value of x. And this x is between -1 and 1. So overall, once we have the conditional PDF y given x, then the conditional expectation y given x is fixed. This will be consider all possible outcomes times the weighting. So the y is from the absolute value of x to 1. Y divided by 1 minus absolute value of x dy. This should be 1 divided by 1 minus absolute value of x y from x to 1. So that is your answer. 1 plus absolute value of x divided by 2. Then we will see some examples, more examples, so you will know how to find the conditional expectation. So 1, 2, 3. I think we have 3 or 4 examples here. First, I want to find this expectation. And we know that x is uniform. And I only know y given x. This random variable is Gaussian with zero mean and variance x squared. But first, when we try to find the expectation, we always use the definition. Okay, here the definition. X times e to the y. Two random variables, then their corresponding weightings here will be the joint PDF. So I consider all possible outcomes x times e to the y. Their corresponding weighting joint PDF xy. X and y, we didn't say that they are independent, so they cannot separate. But what is the joint PDF? And also we have a conditional PDF of y given x. So in this case, we can rewrite the joint PDF. X times e to the y. How do we rewrite that? That is the conditional PDF times the marginal PDF of x. Again, here we can choose x given y. Then I will times the marginal PDF of y. Or this one, depending on my condition. In this case, I only know the PDF of x and then the PDF of y given x. So that's why I choose y given x rather than this part. So here we have my x is from 0 to 1, uniform. And the y given x, it's a Gaussian, so minus infinity to infinity. Zero mean and variance x squared. Oh, I also have e to the y. E to the y, 1 over square root of 2 pi sigma squared, that's x squared. E to the minus y, since I don't have mean, divided by 2x squared. Dy dx. So x is still from 1 and 0 to 1. We need to rearrange this part. The variance is still x squared, But how about the mean? With this, because here I have e to the minus y squared times 2x squared e to the y. No, 2x squared y. So I need to make this as a perfect square. So here we have 1 over square root of 2 pi x squared e to the minus y squared plus 2x squared y minus x to the fourth. Then I also need to times e to the x squared over 2 back. So in this case, we will see this is the integration from 0 to 1. And for this Gaussian, e to the minus y minus x squared overall squared divided by 2x squared dy, and then e to the x squared over 2 dx. What's the result of this part? Using the PDF property again. This is a Gaussian. Mean x squared, variance x squared. But if I take the integration, consider overall, then from the property of one of the properties of the PDF, this integration is 1. So I only have the integration from 0 to 1 x times e to the x squared over 2 dx. Now, since you know how to find the expectation, next, let's see how to find the probability. So for the probability, x is greater than 2. And then I don't give you the PDF of x. Instead, I give you a PDF of y and also x given y. Then how do you find the probability of x is greater than 2? No matter what conditions you have, first, by the definition, how do you find the probability of x greater than 2? From the definition, greater than 2, that means I do the integration from 2 to infinity times the PDF of x dx. Now again, what is the PDF of x? Here we don't know the distribution, but we can think of this PDF as a marginal PDF. So if it is a marginal PDF, how can I get this marginal PDF? Using the joint PDF, right? Joint PDF, you take the integration and sum the y out, then you get this marginal PDF of x. So this is equal to from 2 to infinity. So if you integrate the y out, you get the PDF of x. And the next step, what is the joint PDF? How do I express the joint PDF? I only have a conditional PDF, so use this conditional PDF to rewrite this joint PDF. So x given y times the PDF of y. Again, you can also choose y given x and times the marginal PDF of x, but we still don't know this. And from the question, I know the distribution of x given y and y. So that's why I choose the PDF of x given y times the PDF of y to express the joint PDF. So here we have y is uniform from -1 to 1. So it will be 1/2 y. And then x given y, that's exponential. So that'll be e to the minus yx. So let's separate the x and y. Let me just rearrange that. Take the y over 2 outside. Here I have 2 to infinity, e to the minus yx dx dy. So here we can do the integration. 1 over 2 times y. Here that should be 1 over y minus 1 over y, e to the minus y times x. And your x is from 2 to infinity. And overall, just integrate with respect to y. So you can easily find the answer. Here should be minus 1/4 e to the minus 2y, and your y is from -1 to 1. So 1/4 e to the 2 minus e to the minus 2. Next example, x and y are jointly uniformly distributed on the unique disk. So I give you the joint PMF or PDF. So first, let's find the marginal PDF of x. So what is the marginal PDF of x? Because I need x, I don't need y, so I integrate the y out. We have an integration from minus square root of 1 minus x squared to square root of 1 minus x squared. That's for y. Okay. 1 over pi. And for x, x is from -1 to 1 dy. So it's 2 over pi square root of 1 minus x squared. Now, once we have the PDF of x, then how about the expectation of x? So let's see the expectation of x. Consider all possible outcomes and times their corresponding weightings. That's the PDF of x. So here you have the integration from -1 to 1, x times 2 over pi, and the square root of 1 minus x squared dx. And that's 0 because this function here is an odd function. And since we have the marginal PDF of x, then we can find the conditional PDF of y given x. Because we have the joint PDF and also the marginal PDF of x. So here we have f of xy, the joint PDF divided by the marginal PDF of x. So here, 1 over pi, and then actually your region is the xy in the unit disk, within the unit disk. And the 2 over pi so overall, that's 1 over 2 times square root of 1 minus x squared. And then the y is between 2 square root of 1 minus x squared. And your x is from -1 to 1. Then we can find the expectation, conditional expectation of y given x. Y times the conditional PDF of, because that's expectation, consider all possible outcomes times their corresponding weightings here. That's conditional PDF y given x. So y times 1 over 2 times square root of 1 minus x squared dy. That's 0. And through this example, you can see that actually x and y are not independent because you cannot separate the joint PDF into the multiplication of each marginal PDF. So it is not equal to the multiplication of your marginal PDF. X and Y are not independent. We found f of x here. Actually, you can also find f of y, the PDF of y. That is 2 over pi. Similarly, it's 1 minus y squared. And y is also from minus 1 to 1. But when it times together, you can see when it times together, it is not 1 over pi. So they are not independent. Okay. Last example. I have a CDF, the joint CDF. Now through this joint CDF, first let's find the marginal CDF. CDF of x. How can I find the CDF of x if I have the joint CDF? That means to find the CDF of x, I don't need y, just let the y goes to infinity. So in this case, I have 0 when x is less than or equal to 0, or x squared when x is between 0 and 1, and also 1 when x is greater than 1. Similarly, we can find the CDF of y. So CDF for y, then for x, and then x goes to infinity, then we have y is less than 0, then we can get 0. Y is between 0 and 1, we get 2y minus y squared. And when y is greater than 1, then we have 1. So let's find the probability. X is less than or equal to 2. Intersect that y is less than or equal to 3/4. To write the probability this way, we can also using the joint CDF. That means this is 2 and 3 over 4. So it is 2 times 3 over 4 minus 3/4 squared. Or we can write the joint PDF. So f of xy, that should be 2. And here is the region. Y is between 0 and x is between y and 1. So if you find the probability, actually it is from minus infinity to 2, and from minus infinity to 3 over 4 joint PDF. Let's see. I want, here's the x and y. is 3, 4, and here's 1. 3, 4, and 1. If I do the integration, it's from 0 to 3 over 4, and 0 to x, and then 3/4 to 1, and 0 to 3 over 4. Here's dy dx. From 0 to 3/4, 0 to x, 0 to 3/4. All right, let's take a break, and then we will have an example of talking about the detection problems. So now let's see this detection problem, very classic detection problem. X is a random bit, so it's either 1 or -1. And the probability of having 1 or -1 are all the same, 1/2. And we can draw this x. Here's the x random bit. And then they go to the noise channel. So this is a noise channel. And then we have a noise. This is a random variable, n, that is Gaussian. Zero mean variance 1. And then I have the output. So this output is my random bit plus the noise. And we know that x and n are independent. So suppose we observe y is greater than 0. Then we would like to know whether the signal is more likely to be +1 or -1. Because when I send 1 or even -1, this overall y could be greater than 0. But I want to know which one is more likely to be sent. So here first we should know noise n is Gaussian, but x I don't know. X is just, we don't say that they are uniformly distributed. It is just with probability 1/2 to have 1, 1/2 to have -1. And how about y? What's the distribution of y? Only when x is fixed, if it is 1 or -1, then we know the y is Gaussian. So the conditional PDF y given x, this is Gaussian. So when x is 1, then this is a Gaussian 1 over square root of 2 pi times exponential. The mean is 1 and the variance is still 1. Because now the y is equal to 1 plus n. So the expectation of y will be 1 plus expectation of n, and we know it's 0 mean. So for n, so it is 1. And we can also write it down. The conditional PDF of x, y given x equals minus 1. As 1 over square root of 2 pi e to the minus y plus 1 over 2. Similarly, okay, because here we have minus 1. Minus 1. So my mean is minus 1. So that's why we have y plus 1. So now, given y is greater than 0, then we need to find the probability, because we want to know x, which x 1 or minus 1 is likely to be sent. So x is plus 1 given y is greater than 0. And also I want to find x is minus 1 given y is greater than 0. So first, x is 1 given y equals greater than 0, using the basic theory, that is y greater than 0 given x is 1 times the probability of x is 1. Divided by y given y greater than 0. For x is minus 1 given y greater than 0, then basic theory, y greater than 0 given x is minus 1, which means given x is minus 1%, then my result y is greater than 0 times the probability of your x is minus 1. So we need to find this. So find that first. Y given x, the probability y greater than 0, but given x is 1. Because we know that this probability is Gaussian. And we have our conditional PDF. So that's from 0 to infinity, 1 over square root of 2 pi e to the minus 1, y minus 1 squared divided by 2 dy. That's 1 minus, from minus infinity to 0. One over square root of 2 pi and e to the power 1 minus 1 squared over 2. In this way, we can check the table. Actually, this is the phi 0 minus 1 divided by 1. So if you check the table, you will see the normal distribution table. It is 0.8413. Similarly, we can get x is minus 1. Minus 1 is cent. Then the probability of y is greater than 0. Then you do the same procedure, you get 0.1587. We know this is 1/2 and this is 1/2. So actually we just compare this term, okay? And we know that 1 is cent is more likely because the denominator is the same, okay? But we may be curious about the probability of y greater than 0. So how do we find the probability of y greater than 0? So we can use the total probability law. Total probability law. Then we have the probability of y greater than 0. That is the probability. First, given x is 1, then y is greater than 0. Then we need to times the probability that 1 is cent. Then plus, given minus 1 is cent, then my y is greater than 0. So you'll see that y is greater than 0, actually the probability is 1/2. So here we should say that 1 is cent is more likely. Okay, now here's the question. We know y given x, this PDF is Gaussian, but why not just the PDF of y? Here's the question. Why the conditional PDF of y given x this is Gaussian, but not just the PDF of y Gaussian. Let's see first the CDF of y given x. For the CDF of y given x, that is CDF is a probability. Okay, so this is the probability of your y given x equals x. What is y? Y is x plus the noise n, that is less than or equal to y, given I have a fixed x. So if I have a fixed x, that means I have the noise n plus, this is not randomized, so lowercase x less than y. And this is the probability of n less than or equal to y minus x. We know the random variable n is Gaussian. So, and also this probability of your random variable less than some number, that is your CDF. So when we take the derivative, then we can get the PDF. So here the conditional PDF, that is d CDF y given x dx, dy. Then we have the PDF of n at y minus x, and this is the Gaussian 1 over square root of 2 pi exponential, and then the power is y minus x squared over 2. Then you may ask, then what is the distribution of y? So what is the distribution of y? Let's see the distribution of y, the CD of y. For the CD of y, that is the probability of your y less than some point. We know y is x plus n. And then we have these two terms. This is the function of two random variables. So here's x and here's n. Suppose x plus n like here. You're less than that, so this is your area. So finally, here's a note for this. Y given x equals x. That is the Gaussian with the mean x and the variance 1. And the random variable y is not Gaussian. So here we just mentioned that actually for y, that is the function of two random variables. We just mentioned the multiple random variables, actually just two random variables. Then the next one, the next type of random variables is the function of two random variables. So let's see the function of two random variables. So for a function of two random variables, first, let's see the sum of two independent random variables. So first, consider two independent random variables, x and y, and then also they have the PDFs, fx and fy. And now I have another random variable z. Z equals x plus y. So we want to find the PDF of z. So what is the PDF of z? We can find the CDF first and then take the derivative of your CDF to get the PDF. So let's try to find the CDF of z first. So the CDF of z, CDF is a probability. Your random variable z less than or equal to some point. And we know z is equal to x plus y. So here we have x plus y. And x plus y less than or equal to z. That means my x and y, this random variable pair, is belong to an area. And here this is the area. X and y in the real lines, and x plus y is less than or equal to z. So now, for the CDF of x, CDF of z, we can consider the joint PDF of xy in the region AZ. They are independent. So when they are independent, that means I have x and y dx dy. But we need to check the range. So first, let's draw x plus y. So here, x, y, x plus y. It's this. And this is y. And here there will be z. And this is also z. This red line is x plus y equals z. So what does that mean? X plus y less than or equal to z? Here. This is AZ. Okay, so the x is from minus infinity to infinity. And the y, let's see the y. y is from negative infinity to here. This is, y is from, let's do the x. X is from minus infinity to here. This will be z minus y. And then y will be from minus infinity to infinity. So here it is f over y PDF. And then we have, since they are independent, so we separate that. Z minus y f over x dx. So this is PDF of y. And how about this integration? That is the CDF of x, z minus y dy. We chose to integrate x first, then y. You can do it in the other way around. Or you can do the y first, then x, dy dx. If we do y first, y will be 0 to z minus x, minus infinity to z minus x. So once we have the CDF, then let's take the derivative to get the PDF. So here the PDF d over dz. Okay, so we only care about z. Right, so for z, I still have a PDF of y, and here I have d. CDF of x at z minus y dz dy. So you can see that this is the PDF of y, and here is the PDF of x at z minus y dy. For this expression, you see that actually this is the convolution of your x, PDF of x and y. So now here's a note. So if x and y are independent, then sum of the two random variables, your z, the PDF of z, will be the convolution of your PDF of x at z and also PDF of y at z. Let's see this example. X and y are independent, and I have the PDF of x and PDF of y. Then I want to find the PDF of z, and the z is x plus y. So we know that they are independent, so the PDF of z should be the convolution. So PDF of Z is the convolution. So PDF of X at Z minus Y times the PDF of Y. That is from 0 to Z. And your X PDF of X, Z minus Y times exponential minus Z minus Y. And your PDF of Y, Y times e to the minus Y dy. And then here you get Z cubed over 6 times e to the minus Z for Z greater than or equal to 0. Because we know that X is greater than or equal to 0, right? So Z minus Y should be greater than or equal to 0. And then that's why Z is greater than or equal to Y. And for Z is less than 0, my PDF is 0. So overall, my PDF of Z is Z cubed divided by 6 times e to the minus Z